Sir's chemistry classes. Today it is the fourth session of structure of atoms, and we will learn an interesting thing called exchange energy, which is the basis of Hund's rule of maximum multiplicity. So in the first session we have already learned that half-filled and completely filled orbitals are more stable than any other electron configurations. Now, why this is so? We have to understand it. You see, I have drawn a configuration 2p3. There is an exchange. You see, there is exchange between this. There could be exchange between these two electrons. One exchange. There could be exchange between these two electrons. Two exchange, and there could also be exchange between these two electrons. Okay. So there are a total of 3 exchange. And now the formula of exchange energy Ex is based on the combination rule Nc2, and is given by n into n minus 1 by 2 k, whereas k is a constant. Now you see, for 2p3 configuration, the exchange energy turns out to be 3 unpaired electrons in parallel spin. So 3 into 3 minus 1 by 2, that is equals to k, that is equals to 3k. So the exchange energy of 2p3 orbital, 2p3 configuration turns out to be 3k. On the other hand, you see, if the configuration would be like this, one, 2 and 3, then one exchange is only possible since only 2 electrons are in parallel spin, that is rotating at the same directions. Therefore, E exchange equals to n into n minus 1 by 2 k, that is equals to 2, there are 2 electrons in parallel spin, so 2 into 2 minus 1 by 2 k, that is equals to k. Now we know that greater the exchange energy, greater will be the stability. So if the 2p3 configuration, in 2p3 configuration, if the electrons are parallel in spin and unpaired, then the exchange energy is greater, 3k. Whereas when the electrons are put in this manner, first one orbital is occupied by 2 electrons, then the second one, then the exchange energy would be equals to k. Therefore, this 2p3 configuration, where all the electrons are parallel in spin and unpaired, is more stable than that in case of the second one. And this is the basis of Hund's rule, which states that in the ground state of an atom, as long as there are vacant degenerate orbitals, the electron will try to remain unpaired and parallel in spin, and not like this. This is contrary to the Hund's rule, and this is the actual electron configuration. Now from this, we can find out the exchange energy of other orbitals, like completely filled d orbitals, d10. The configuration is like this. You see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the exchange energy is 5 orbitals are 5 electrons are at the same spin, and on 5 electrons, so 5 into 5 minus 1 by 2k plus another 5 electrons are in the same spin, therefore 5 into 5 minus 1 by 2k, which turns out to be 10k plus 10k equals to 20k. On the other hand, in the half-filled d orbital, you see here d5 configuration, 1, 2, 3, 4 and 5, 1, 2, 3, 4, 5. The exchange energy is given by 5 into 5 minus 1 by 2k, that is equals to 10k. So here you see, on the other hand, you see d4 configuration. In case of d4, the exchange energy is given by 4 into 4 minus 1 by 2k, which turns out to be 6k. So here you see D5 configuration is more stable than D4 configuration, whereas the completely filled d orbital is rather more stable with the exchange energy of 20k. That's why D5, D10 configuration is more stable than D5, that is half filled. Completely filled d orbital is more stable than half filled d orbital, which is in turn more stable than D4 configuration. Similarly, in case of 2p3, the half filled orbital, the exchange energy is EH equals to 3 into 3 minus 1 by 2k, which becomes equals to 3k. But in case of completely filled p orbital, you see 2p6 configuration 1, 2, 3, 4, 5, 6. The exchange energy will be for first 3 electrons in parallel spin 3 into 3 minus 1 by 2k, plus for the next 3 electrons in parallel spin 3 into 3 minus 1 by 2k, which turns out to be 6k, which is greater than that of 3k. That's why we can say that 2p6, that's completely filled p orbital, is more stable than half filled p orbital. This is the case of the basis of Hund's rule, where we could find out the relative stability of the orbitals having completely filled or half filled or partially filled. Now, knowing about 4 types of quantum numbers, we are now going to assign the quantum numbers to the electrons and thereby finding out the basis of Pauli's exclusion principle. So here you see I have drawn an electron configuration of 2p6. Now 2p6 is equivalent to n L to the power x, where n is 2. Here the principal now quantum number is 2. There is an equality, and L, that is the sub-energy level, and x is the number of electron, 6. You could compare it very easily. Now for n equals to 2, L can have 2 values, and those are 0 and 1. Here 1 means p orbital, we have drawn this p orbital. And for L equals to 1, that is for p orbital, in p is sub-energy level. The value of m, that is value of m, are minus 1, 0 and plus 1. That is, there are 3 orbitals in this p sub-energy level with values minus 1, 0 and plus 1. So every electron will have 4 sets of quantum numbers. 4 sets of quantum numbers. You see, for this electron, n equals to 2. All the cases, n equals to 2, n equals to 1. m equals to here minus 1, and s equals to clockwise direction rotation, which gives the number plus half. And for this electron, n equals to 2, n equals to 1, m equals to again minus 1, but s equals to a counterclockwise direction electron rotation gives a value of minus half. For this electron, you see n equals to 2, l equals to 1 again, m equals to here now you find the value of 0, and s equals to again plus half for clockwise rotation. And for this electron, n equals to 2, l equals to 1, m equals to again 0, and s equals to plus half. For this electron, you see n equals to 2, l equals to 1, m equals to here plus 1, and s equals to clockwise rotation plus half. And for the last electron, you see n equals to 2, l equals to 1, m equals to plus 1, and s equals to minus half. So it is evident to us that for these 6 sets of quantum numbers in the same atom, there are no such values, sets of values, those are same. One or more than one values of the quantum numbers are unequal in each cases. So this is the basis of Pauli's exclusion principle, that in an atom the sets of 4 quantum numbers cannot be equal for any 2 electrons. This is one of the corollary of Pauli's exclusion principle, But the original statement of the principle is an orbital cannot accommodate more than 2 electrons. The fact shall be revealed by the explanation. Suppose 3 electrons are there in one s orbital, if it were possible. Now the electron spin will be like this, one clockwise, one counterclockwise, and another may be counterclockwise or clockwise. I am taking it clockwise, suppose. Now for this, n equals to 1. For this s orbital, we know that n equals to 0. We have already learned this. n equals to 0 for s orbital, so m equals to also 0, and s equals to plus half. Plus half. Now for this electron, n equals to 1 again, n equals to 0 again, n equals to 0, but s equals to minus half, counterclockwise rotation. And for this one, again clockwise rotation, you see, n equals to 1, n equals to 0, n equals to 0, and s equals to again plus half. So these two values, this one and this one, are the same, which means these two are the same electrons. So there are only 2 electrons. This one are the same, this one and this one. So an orbital cannot accommodate more than 2 electrons. It has been proved by, it has been shown or verified by this electron configuration. So guys, we have already learned how to assign the quantum numbers of different electrons. Now I am going to give a small problem to you. You see, I am writing 4 sets of quantum numbers. A, n equals to 4, n equals to 3, m equals to minus 3, s equals to plus half. Next one, n equals to 4, n equals to 4, n equals to 4, m equals to plus 3, s equals to minus half. C, n equals to 5, l equals to 3, you see, m equals to minus 2, s equals to minus half. And the last one, n equals to 5, l equals to 4, m equals to 0, s equals to plus half. Now out of these 4 sets of quantum number, which is not possible for an electron, you see the first one. If the value of principal quantum number is 4, then L can have value 3 because it is the maximum value, n minus 1. And for a particular value of L, m can have minus L to plus L values. That is, here it is minus 3. Okay, it is also correct. And S can be plus half or minus half, anyone. For n equals to 5, we find that L has a value of 0 to n minus 1. So 3 is possible, permissible value. And for particular value of L, n equals to 3, m can have value of from minus 3 to plus 3. So minus 2 is also possible and minus half is also possible. Here for n equals to 5, you see L can be 4, n minus 1, and m for n equals to 4, the value of m are minus 4 to plus 4, so 0 is possible, and plus half is also possible for S. But for this one, you see n equals to 4 and L equals to 4. Here the contradiction begins. L cannot carry the value of 4 because L must have the maximum value 1 less than the value of n. Therefore, this set is not possible for an electron in an atom. Okay? Sure? So, we have, I think, understood how to assign the quantum numbers, and about the quantum numbers very empirically. There are many problems, many concepts regarding these quantum numbers which is not in our scope at all. So, the syllabus which I like to confine is represented here. I think you will go through it rigorously and could understand the quantum number at the basis of all theories and the electron configuration. So till then, goodbye and good luck.